Well, welcome to this video. What we are going to do in this video is basically model me playing the 17th hole at TPC Sawgrass as a Markov chain. If you're not familiar with golf at all, basically 17th hole at TPC Sawgrass is a par 3 with an island green, which basically means you step up to the tee, you know the green is 130 yards away, you know what club you hit 130 yards, and you take your swing and you either end up on the green or you put it in the water. So there's not a lot of strategy involved in terms of club selection on this hole because it's not a par 4 or par 5 where you're choosing whether or not to lay up. So it lends itself to being modeled as a Markov chain as opposed to a Markov decision process. And ultimately what we're interested in determining or capturing is formulating me playing this hole as a Markov chain and then using the Markov chain to determine whether or not I make par or better on that hole. So whether or not I put the ball in the hole in three or fewer shots. And so I've kind of listed within the problem description the various places that you can end up, your ball can end up, or my ball can end up. I mean, you start the hole on the tee, you take your swing, you either put it on the green or you put it in the water. If you put it in the water, you end up having to hit a shot from the drop zone. If you put it on the green, we've kind of approximated 4 different regions of being on the green. We're either 20 feet away from the hole, 20 feet or more away from the hole, we're between 5 and 20 feet away from the hole, we're under 5 feet away from the hole, and then we can ultimately be in the hole. So what we want to do is we want to formulate this problem as a Markov chain. And in order to start going in terms of the Markov chain formulation, we need to start identifying what are the states we're going to include within the Markov chain. And it's kind of natural to start thinking, well, the ball is going to end up in different locations as I'm playing this hole. So at minimum, we should have states representing each potential location of the ball. So what we're going to just start doing is we're going to list the potential locations of the ball along with some shorthand for them. So in terms of locations of the ball, we can be on the tee, and we're going to shorthand that with capital T. We can the ball can end up in the drop zone, or a new ball would end up in the drop zone. We hit our ball into the water and then we go to the drop zone. We can then also be on the green and be 20 plus feet away from the hole. We're going to shorthand this as L, which means that we're a long distance away from the hole. We can also end up being 5 to 20 feet away from the hole, and we're going to shorthand that as M, which basically means we're medium distance on the green away from the hole. We can be under 5 feet away from the hole, and we'll shorthand that as S. We're in a short distance away from the hole on the green, and then we can also be in the hole itself. So we can kind of list these locations and start getting us thinking about what are the states of the Markov chain going to be. And one thing that we're interested in knowing is basically, am I going to hole out in 3 or 4 fewer shots? So the ball being 5 feet away or under 5 feet away from the hole does not provide me a full picture of whether or not I have a shot at having 3 or fewer shots on this hole. So basically making par. Because if I am putting and I've already hit 3 shots, then I'm clearly going to make at least a bogey or worse. But if I've only hit my tee shot and I'm under 5 feet away, then I have a couple opportunities to try and put the ball in the hole and still make par or better. So the fact that the ball being in a particular location does not give us the full picture associated with how we played the hole. That should indicate that we need to have a larger set of states than simply the locations of the ball. And that's what we're going to end up doing is we're going to end up kind of discussing that we're going to need a couple different versions of the medium and short green distance locations in order to properly capture the state of the Markov chain. So what we'll do is we'll start defining the various states of the Markov chain. We're going to have the T state, which basically means that that's where our Markov chain is going to start. And then we're going to have the drop zone state as well. And then what we're going to do is we're going to have a state that we're going to designate L1, a state we're going to designate M1, and a state we're going to designate S1. And basically what these three states signify is that I am on the green and I've only hit one shot. So L1 means that I am on the green, I am 20 plus feet away from the hole, but I've only hit my tee shot so far. M1 means that I basically put my tee shot 5 to 20 feet away from the hole, and I still have 2 more shots to get the ball in the hole to make par or better. S1 means that I hit my tee shot really, really close to the hole. I'm under 5 feet. And then what we're also going to have is we're also going to have states M2 and S2, which represent being the medium distance away and the small distance away from the hole after 2 shots. One reason we do not have an L2 is that it's going to be impossible with the way we've defined our transition probabilities, or the transition probabilities, to be 20 plus feet away from the hole after 2 shots. Basically, if I put the ball on the green with my first shot, then I'm going to always be able to putt it to under 20 feet. So that's why we don't have an L2. And then the thing is, we don't need M3 and S3. And the reason why we don't need M3 and S3 is that if I am on the green after hitting 3 shots already, then I know I'm going to make bogey or worse. So if I were to be in state kind of M3, I know that I'm going to be making my bogey or worse, so I don't need that. So we have M2, S2, and then we're going to add in 2 more states. We're going to add in our par or birdie state, and we're going to shorthand that PB. So that basically means that I hold out in 2 or 3 shots, and then we're going to have our bogey or worse state, and we're going to signify that or kind of view that as B+. So we have our states, and now what we need to do is we need to define the transition probability matrix. So basically for each state, we need to determine, well, what are our transition probabilities to every other state. So let's start with the T state and figure out the probability that if I'm in the T state, I end up in the various other states. So I have no chance at being on the tee after I take 1 shot. So the transition probability from T to T is 0. Now I do have a positive transition probability of starting at the tee and ending up in the drop zone. Basically 25% of the time I end up in the drop zone because I put my ball in the water. And then I have a 60% chance of hitting my ball onto the green and being 20 plus feet away. I have a 10% chance of hitting my ball onto the green and being 5 to 20 feet away. And then I have a 0.05% chance of hitting my tee shot and being 5 feet or under. I can't end up being on the green after 2 shots with from just the tee, because that only represents essentially 1 swing, the tee transition. So I have a 0-0, and I can't hole out, so I end up with a 0 to each of the states at the end as well, the par or birdie state and the bogey or worse. Now we can look at the drop zone. Now the drop zone is kind of interesting because from the rules of golf, you hit the ball in the water, you take a penalty stroke, and then you drop the ball, so you're actually hitting your 3rd shot from the drop zone. So that basically means if I don't hole my out from the drop zone, I'm going to make bogey or worse. So we have a 0 transition probability to the tee. We can't. So technically speaking, if I hit the ball in the water again, I end up in the drop zone again. But like I said before, if I don't hole out from the drop zone, I'm going to make bogey or worse. So we can actually put zeros in basically everything besides the par or birdie state or the bogey or worse state. So 0.01% of the time from the drop zone I hole out and make my par or better. And then 99% of the time I end up having to take another shot after being in the drop zone. So 99% of the time I'm going to make a bogey or worse. Now we look at kind of L1. Well, if I'm on the green after 1 shot, so after my tee shot, I cannot end up back on the tee. I cannot end up in the drop zone. I cannot end up in L1, M1, or S1 because I'm going to take a 2nd shot before I kind of move. So I cannot end up being in a state where I've only taken one shot when I transition out of L1. So basically, if I look at kind of the historical putting probabilities, 15% of the time, so 0.15, I hit my shot from L1 and end up in a medium distance away from the hole. So, and then 0.8% of the time, I end up hitting my second shot and being less than 5 feet away from the hole. And then 0.05% of the time, I actually hole out from L1, from the long distance. And then I can't currently make a bogey right now because I will always transition to either closer to the hole or actually holing out. So for M1, we do something really similar. M1, I can't end up in the T, the drop zone, in any of the 1 states, but I can end up in the 2 state with 0.05. So basically 5% of the time, if I'm a medium distance away, I putt it and end up being a medium distance away. 80% of the time, I end up being from the medium distance after 1 stroke, I end up being at a short distance after 2 strokes, and then 0.15% of the time I actually hole out. And we end up with 0 making a bogey because I'm hitting my second shot. I still have that opportunity to hit the third shot. So for S1, basically I end up with zeros again. I cannot go from a short distance away from the hole to a medium distance. And then 15% of the time I end up a short distance away, and then 85% of the time I end up a long distance away. So, and then 0% of the time I end up bogey or worse right now, or transition to the bogey or worse state, because again, I'm hitting my first shot, and then I still I'm hitting my second shot from S1, and then I still have an opportunity to hole out in 3 or few shots. Now M2, what becomes interesting is at M2, I'm hitting my third shot. So I am either going to hole out and make my par or better, or I'm going to miss it and know I'm going to make bogey or worse. So we're going to have all zeros except for the par or better state and the bogey or worse state. And so basically, I only hole out 15% of the time if I'm a medium distance away. And then I miss my putt 85% of the time. So I either end up a medium distance away or a short distance away. Doesn't matter. I'm going to have to hit a 4th shot or more. So I end up 85% of the time being in this bogey or worse state. And then S2, again, I either hole out or I don't hole out. So I hole out 85% of the time if I'm under 5 feet. If I hole out with my third shot, then I make my par. Otherwise, I make bogey or worse because I'm still on the green and I'm hitting my 4th shot. Now, what becomes interesting is the par or better state. Par or better state is an absorbing state. Once I'm in it, I'm done. I finished the hole. My Markov chain will stay in that state forever. So this par birdie state transitions to itself with a probability of 1, and has transition probability 0 everywhere. Now for the bogey or worse state, the bogey or worse state is an absorbing state as well. If I'm going to make bogey or worse, I'm going to make it and I'm going to stay in that state forever. So we have zeros everywhere except for a positive 1 to itself. So this is our Markov chain. This is our transition probability matrix. I'm going to show a very messy transition probability diagram. As you can see, it is not pretty looking. Basically, transition probability matrix diagram, we draw a node for every state, and then we have arcs connecting to nodes, or if we have an arc connecting node I or state I with state J, if there's a positive probability of transitioning from state I to state J. So basically, I can look at the T state, and I have 4 arcs leaving the T state, 1 going to each of the 4 possible transitions out of T. So I figured I'd show this as a nice kind of visualization should you have kind of a less complicated Markov chain. So now what we're interested in doing is we're interested in taking this Markov chain and figuring out the probability that we're actually going to make par or better. Another way of putting that is we're going to start in the T state. I want to know the probability that eventually I'm going to get absorbed by the PB state, by the par or better state. So there's a series of equations that allow us to make this calculation, and we're going to start writing them out. So remember, we define F to be the probability that I start in state T and end up being absorbed by the par birdie or par or better state. And this probability, the way we can calculate this, or the way the equation is defined for this probability, is that we look at all the possible transitions out of the T state, and we basically know that we have to transition out of the T state. We end up in another state, and then from that state, we have a probability of ending up in the PB state. So let's kind of start constructing this. Let's look at the drop zone. We have a 25% chance that we are in state T and we transition to state DZ. And then we have from there, the probability that we start in DZ and transition to PB or end up being absorbed by the PB state is defined to be F of DZ, comma, PB. And then we also have a 0.6 probability of transitioning from the T state to the L1 state. And then the probability of being in the L1 state and ending being absorbed by the PB state is defined as FL1 PB. And then we have a 0.1 probability of being in the T state transitioning to the M1 state, and the probability of being in the M1 state and ending up in the PB state is PB, or is FM1 PB. And then we also have a 5% probability of starting in the T state, transitioning to the S1 state, and then we have from the S1 state, we have the probability of being in S1 and absorbed by the PB state is FS1 PB. So basically what we are doing in this equation is we're looking at the transition probability row out of the state T, and then we're taking each of the probabilities, transition probabilities, and multiplying it by the F of the state J we've transitioned to, comma, the PB state. So really similarly, if we look at F of DZ, so F DZ, comma, PB, we only have two transitions out of the drop zone state. We have a 1% chance of transitioning to state PB, so we multiply 1% by F PB, comma, PB, and then we have a 99% chance of transitioning from DZ to B plus, and then so 99 times F of B plus PB. And we're going to have to do this for all of our states, so we can then look at F of L1, comma, PB, and that is equal to 0.15 times F of M2 PB plus 0.8 times F of times F of S2 PB plus 0.05 times F of PB, comma, PB. And then we have to do this for F of M1 PB. And that is equal to, so we look at what the transition probabilities out of M1 is. 0.05% of the time we end up in state M2 PB. And then 0.8% of the time we end up in state S2, so we multiply 0.8 by FS2 PB, and then we have a 0.05, and I completely did this wrong, but it'll save us some time, so F PB, comma, PB. I'm going to copy this real quick. So F of M1, we have a 15% chance of being in the state of transition to state M2. And the reason why this saves us time is I just misread. Sorry, I had that right. So it should be 0.05. I'm looking at the wrong rows. And then we had a 15% chance of holding out and transitioning to the PB state from M1. So now we can look at L1. For L1, we cannot transition to the M2 state, but we can end up in the S2 state, and we end up in the S2 state 15% of the time, and then 85% of the time we end up holding out. So a little bit simpler, and we're kind of getting towards the simpler set of equations. We can now look at f of m2 pb. Well, f of m2 pb, I either end up 15% of the time, I end up in the pb state, so I multiply 0.15 by f of pb, and then 85% of the time, I end up in the b plus state, so I multiply 85.85 times f of b plus pb. And then f of S2, and I am making minor mistakes everywhere. This should actually be f of S1. Sorry for that mistake. So f of S2 pb is, we're looking at the where we can transition out of state A2. So 85% of the time we transition to state PB. So we multiply 85 times PB, f of PB, comma PB, and add that to 0.15 times f of b plus, comma pb. And now we're at a very nice kind of, the last two states are actually really easy. So f of pb, comma pb, I mean, by definition, f is the probability of starting in a particular state I and ending up in the absorbing state J. So if I start in the par or birdie state, the probability that I'm going to end up being absorbed by the par or birdie state is equal to 1. And then the probability that if I start in the bogey or worse state, that I end up being absorbed in the par or birdie state is 0. So we have a couple options. We've defined this, and again, I mean, what we are doing is we are looking at the transition probability. So in order to get, say, fm1, comma pb, what we did is we looked at the transition probability matrix out of M1, and we have taken each positive probability and into state J and multiplied that probability by f of j, comma pb. So there's a 0.05% probability that we're in M1 and we transition to M2, and so we take 0.05 and multiply that by f of M2, comma pb. And there's an 80% chance that we move to S2, so we take 0.8 and multiply that by f of S2, comma pb. And then there's a 15% chance that we end up ending in the pb state. So this series of equations, for this Markov chain, I mean, we could plug it into Solver, we can solve it that way, or this isn't too bad to solve by hand because just kind of the way this, the fact that we're kind of always moving towards the ending states or the absorbing states. So we know that by having fpb, comma pb equal to 1 and fpb plus, comma fb plus, comma pb equals 0, we can solve for these, the M2 and S2 states, very easily, and we can actually solve for the DZ state as well. So basically what we can do is we can do a substitution for this particular state. Well, we know that we get a 0.85 times 1 plus a 0.15 times 0. So we end up with a probability of 85% of the time, if I'm in state S2, I make par or better, and that makes sense. I mean, if I'm in S2, that means I'm 5 feet away from the hole, hitting my third shot. 85% of the time, I hole out in that. For f of M2, we get a lower probability. I mean, basically, f of PB, comma PB is 1, f of B plus, comma PB is 0, so we end up with a 0.15 probability here. And then f of DZ, comma PB, well, we end up with a very low probability of 0.01. So what we can now do is we can kind of make some substitutions here. I mean, if I look at f of S1 PB, I need to know f of S2, comma PB. I know that it is equal to 0.85, and then I know fpb, comma pb is 1. So this is going to be equal to 0.15 times 0.85 plus 0.85 times 1. And that is, I forgot a point. So we have a pretty high probability of being in state S1 and making par or better. And then we can now look at f of m1. This is going to be equal to, we know m2 comma pb, so we take 0.05 times the 0.15 that we solved for f of m2 comma pb, add that to the 0.8 times the f of s2 comma pb, which we just determined to be 0.85, and then we add in the last 0.15 times 1, because we can hole out. So we have an 83% chance of hitting, if we hit our tee shot onto the green, of making par or better. And then we have to do one more of these for, if we're really long after a tee shot, we end up in state FL1 comma PB. So kind of plugging in what we've already solved for, we're going to multiply 0.15 by 0.15. And then we're going to add that to 0.8 times 0.85. And then we're going to add that to 0.05 times 1. And what is nice is, in order to know the f of TB, I needed to know f of t comma PB. I need to know f of DZ comma PB, which is 0.01. I needed to know f of L1 PB, which is 0.7525, and then I needed to know f of M1 comma PB and f of S1 comma PB. So in order to get f of TB, f of t comma PB, this is equal to 0.25 times 0.01. Basically, I hit it into the drop zone and then make par better, plus 0.6 times 0.7525 plus 0.1 times 0.8375 plus 0.05 times 0.9775. So looks like 58% of the time I'm going to start in the tee position and make par or better. So now that's kind of nice. We have that estimate. Now the question is, can I determine f of t comma b plus? So how often am I going to make bogey or worse? Well, I could create a series of equations really similar to this. The main difference would be, obviously the absorption probabilities would flip if I'm going to make the f of b plus comma b plus is going to be 1. But one thing I can recognize is that I have two absorbing states in this Markov chain. I'm going to end up in one of them. So if I end up in par or birdie or par or better 58% of the time, I'm going to end up in the bogey or worse state 1 minus 58% of the time. So 41% of the time I'm making bogey or worse. Now, obviously, we've simplified this a lot. I'm not interested in, are we going to make a birdie? Are we going to make a par? Are we going to make bogey, double bogey, triple bogey? The Markov chain gets really, really messy because you have to then start defining like L1, M1, S1, then L2, L2s, and L3s, and L4s, and it just gets kind of really messy, and then your absorbing states would be each potential stroke. So that kind of ends this discussion. I'll see you guys next time.